Okay, we are in the next part of this dimensions chapter. You might have understood how to write the dimensions for some of the physical quantities by writing some dimensions for some of the physical quantities by using the basic physical quantities like mass, length, and time. We wrote the dimensions for certain physical quantities, and here there are certain other quantities like thermal quantities, electrical quantities, and magnetic quantities, and just we'll go for a practice with them. First, look at here. This quantity here is the temperature. If just this is a quantity which doesn't have any mass, so zero dimensions in mass, there is no length, zero dimensions, and time also zero dimension. And only one is K, that is how this temperature, this is a fundamental quantity and is represented by K. You can write like this or simply you can make it like this, no problem. Next is heat energy. Here heat energy is a form of energy. So we have to write the dimensions for the energy. Energy is nothing but the work. So how we get these dimensions for the energy means by the work. So how to write the dimensions for the work? Using the formula W is equal to F dot S. F is the force. Force is mass into acceleration into S. S means it is the displacement. So this is the displacement. And this is the force. And force is given by the formula mass into acceleration. Displacement. This displacement is nothing but the length. So L to the power of 1, already loaded here. And mass, this is a basic fundamental quantity, m1. And acceleration already we wrote it is, for acceleration it is L1 t power minus 2. How we got this? It is the velocity by time. So velocity is L1 t power minus 1 by t. So it is L1 t power minus 2. So for acceleration, so it is L1 t power minus 2. And again here it is one L1 is there because of this displacement. So it is M1, L1, L1. So it becomes L2 and t to the power of minus 2. So these are the dimensions for the heat energy. Heat energy or any other form of energy, you can go in the same manner. Any other form of energy, it's an energy. How can we just get the energy? Energy is nothing but the work. So what is the, how to write for the work? Just remember the formula W is equal to F dot S. What is F? Force. Force is mass into acceleration. S is the displacement. And finally we got the dimension formula like this. The next quantity is specific heat capacity. So specific heat capacity, you remember the formula Q is equal to ms delta T, and this is your specific heat capacity, or simply as specific heat. You might already touch the specific heat in your other classes. Remember this formula, Q is equal to ms delta T. What is this Q? Heat energy. What is this M? Mass. Specific heat. This is the change in the temperature. The change in the temperature. So actually we should write like this, ms delta T. Okay, right. Now I want this S. So S is equal to Q by M. Delta T is nothing but the temperature itself. Change in the temperature is temperature. So Q, it is energy. So we got the energy here already. Here it is M1 L2 T power minus 2. And mass is M1, and here it is, this is the temperature, not the time, temperature. So it is K. So now this goes away, so it is L2 T power minus 2 and K power minus 1. Sometimes instead of this K, we use theta also. Okay, so or you can write it as L2 T minus 2 theta to the power of minus 1. Okay, so generally just follow this instead of going with the theta. So now here, by remembering this formula, we are able to write the dimensions. So generally if you don't know if you don't, generally we don't remember the dimensional formulas because we have so many physical quantities, and there are for every physical quantity we have to write the dimensions necessary for us to know the dimensions. So for every physical quantity we cannot remember the dimensions in straightforward. So the only way is just to get it by using the formula Q is equal to, so as we did it here, Q is equal to ms delta T. Next one is latent heat, Q is equal to ml. Latent heat, you remember latent heat, hidden heat. When substances are changing its state from solid to liquid or liquid to gas. So when, suppose if you are melting the ice at 0 degree centigrade, that means you are supplying some amount of heat, and when you are supplying some amount of heat, this ice changes to water at 0 degree centigrade, but you are supplying some amount of heat. What happened to this heat? This heat we are not able to find out or observe in thermometer. That is absorbed by the system to change its state. So this is the hidden heat. This, instead of hidden, we use the word latent. So latent heat. Similarly, when the matter is changing from liquid to gas, so if you just take the water at 100 degrees centigrade, and if you are providing some more amount of heat, it changes its state. It changes to steam at 100 degrees Celsius. So now, even though you are supplying the heat, that heat is not shown on your thermometer or when you are making some observation. That means that heat is hidden in the system. Okay, used by the system to change its state. Instead of raising the temperature, it is used to change its state. That we will be calling it as the latent. Okay, so like there we use that, and there you might have come across this formula Q is equal to ml, where Q is the heat energy, m is the mass, L is the latent heat. Okay, so this is heat energy, and this is the mass, and this is what you are calling it as the latent heat. So we want this L here, so L is equal to Q by m. Already we wrote the formula for Q here. It is m1 L2 T power minus 2 by, this is mass, so it is m1, so it is L2 T power minus 2. So these are some important quantities. Initially what you have to know related with this thermal. Later we will be coming up, when you are going through the different chapters in this academic year, you will come across some more quantities. At the time, we will learn the formula there itself and write the dimensions. Once if you understand the basic things, then you easily go with the other things. And the next one is coming to the electrical quantities. See here some basic electrical quantities are given, which you might have faced or come across in your earlier classes. It is your electric current. So electric current itself is a fundamental quantity. That means it cannot be derived from either from mass or length or time. So by that we can say it is 0 dimensions in mass, 0 dimensions in length, 0 dimensions in time. And directly now we have to represent electric current using its symbol itself as A or I. So I to the power of 1, or if you don't represent it, nothing happens. Nothing means, if nothing is there, it means that power to the 1 is there. You can write like this, or simply you can write it as I. So that is electric current. And next coming to electric charge. So this electric charge is not a fundamental quantity, it is a derived quantity, and you can remember the formula electric charge Q is equal to IT. You have learned it in your 10th standard. Q is equal to IT. So this Q is the charge, and this is the electric current. Better make it like this. So this is the time. So we want this now here. So already this is, sorry, we want this Q here. Directly we can go like this. What are the dimensions of I? Electric current, I itself, because it is a fundamental quantity. So I, and time is T. So this is the dimension formula for electric charge. And coming to the electric potential. Electric potential. You already know about this electric potential. It is, the electric potential is the work done per unit charge. Work done per unit charge. That means the amount of work done in bringing charges from somewhere to that point is your electric potential. So we remember the formula, W is equal to VQ. So this is the work, and this is your electric potential, and this is your charge. So we want this. So V is equal to W by Q. What is work here? Already we just did somewhere work here. It is M1 L1 T power minus 2. So M1 L1 T power minus 2, and Q, it is IT. So it is M1 L1. This comes to the numerator, T power minus 3, and this comes to the numerator, I to the power of minus 1. So these are some of the important physical quantities, some of the physical quantities in physical electrical quantities. Okay, now just pause the video and take the screenshot. So here some more important quantities are given here. Actually here we are going with the practice. Whatever the quantities you know, you heard when you are coming across the various chapters in your early classes, and this just practice and remember what the formula you are using, and then and then later when you are coming through the different chapters in this 11th standard and in the 12th standard, and whenever we come across a physical quantity, there certainly we will write the dimensions for it, so that it will be very useful for you and will be as a practice for you. Okay, so whatever we have discussed in the earlier session, and now we just practice them and keep it in your mind. Okay, now just these two are also the electrical quantities, resistance and resistivity. You know about the resistance. So now how to write the dimensions for this? So here certainly we have to go with a formula which helps to extract the resistance from different physical quantities. So it is, you know very well, the Ohm's law, V is equal to IR. Here lies your resistance, and V is the potential, and I is the electric current, and here R is your resistance. This is your resistance, so R is equal to V by I. Potential, just before the earlier we just talked about this potential. We have, for potential we have extracted from W is equal to VQ, V is equal to W by Q. So it is W by Q. So this comes to the denominator I. And W, you know how to write the dimensional formula for W. W is equal to F dot S, and F is MA. So M, A, and S is S itself. So it is, don't read it as the mass, MAS. So this is M1, L1. For acceleration it is L1 T power minus 2, and it is L1. So it leads to M1 L square T power minus 2. So this is the dimensional formula for work. So it is, and I'll write it here, M1 L square T power minus 2, and for Q it is IT and I. So M1 L square T power minus 2 I square. So M1 L square, this T comes to the denominator, T power minus 3, and I square comes to the numerator, it is I to the power of minus 2. Okay, so now very simple, isn't it? So if you remember this expression, already you know very well Ohm's law. Once resistance means, just in your mind it comes, the expression will just strike into your mind as the Ohm's law, that is V is equal to IR, and from there R is equal to V by A. V, from where we can extract this V? From W is equal to VQ. We know the dimensions of, how to write the dimensions for W, F dot S, what is F, M. So all these things, just by the practice you can that stores in your brain. Okay, you just take some, you just go take your 10th class textbook or your 9th class textbook and just take some quantities, whatever you come across, like velocity, acceleration, displacement, force, and torque, couple, and moment of force. So whatever the quantities you find there, just take that, and besides that write the formula and write the dimensions. So by this you will be helped in by two ways. One is remember just practicing the formula and as well as writing the dimensions of it. Okay. So now this is the way. Next is the resistivity. How to write for resistivity? Just I'll make it here. Resistivity. Or you might write it as specific resistance. Both mean the same. Specific resistance. What is this specific resistance? And immediately if I say specific resistance, 10th class, I just stress the sentence for you. The specific resistance, immediately if you say specific resistance is constant for a material, and there use the symbol rho, isn't it? So if you just get into your mind the symbol rho, you have only one formula which you are having, the rho. What you have learned, a formula related with the rho, that is R is equal to rho L by A. So what is this R? Resistance. What is this rho? Your specific resistance. What is this L? Length. What is this A? Area of cross section. That means area. Area of cross section means here we consider it as area itself. Finished. So now what is that here? You have to write for rho. So bring it this and take all the other things other side. Rho is equal to R into A by L. Resistance. What the formula got for resistance here? It is M1 L square T power minus 3 I power minus 2. Area, it is L square. Area, length into breadth, that is L square, and length is L. So M1 L square L to the power of 4. If it goes to numerator, it becomes minus 1, and L to the power of minus 3, T3, I to the power of minus 2. Okay, you just make a practice. Instead of just seeing this, you just go through this. You know the formula for the resistance, and you know the area. For this, when you are writing for the resistance, don't look the dimensional formula there. You practice the dimensions using the formula and write there, and write the dimensions. So here, resistivity. Okay, remember the formula is equal to rho L by A. Okay, so that is regarding the resistivity. And here is one more quantity you know very well, acceleration due to gravity. How to write the dimensions for the acceleration due to gravity? Do you remember any formula for it? So you don't get any formula into your brain immediately. But one thing it is, acceleration due to gravity is nothing but it's an acceleration. It is also an acceleration. Earlier I said you were writing about heat energy. Heat energy is nothing but it's a form of energy. It's an energy. If you are able to write the dimensions for energy, you can write the dimensions for heat energy. What are the dimensions for light energy? Light energy is a form of energy. If you are able to write the dimensions for energy, the same thing it can be used there. Similarly here, acceleration due to gravity is also an acceleration. Okay, so acceleration means L1 T power minus 2. That's it. Okay, and next is the pressure. You know very well about this physical quantity, pressure. Pressure, what the formula you get, you remember it as pressure is equal to force by area. Pressure is equal to force by area. Again the same thing, force you know, F is equal to MA. F is equal to MA. So M into A. What is this M? Mass. What is this A? Acceleration. So it is an area. Area means it is length into breadth. That is length into breadth means length into length. Breadth is also considered as a length. So now it is M1 L1 T power minus 2 and it is L square. So it is M1, it goes to numerator. So minus 2 plus 1, minus 1. L1, it goes to numerator, L power minus 2. So it is L to the power of minus 1. Okay. So now it is L to the power of minus 1 and T power minus 2. So like this we can write the formula for, because already you know how to write the dimensions if you know the basic fundamental quantities. That means once if you remember the formula, automatically you can write down the dimensions with the practice. Next is universal gravitational constant. Here you are having small g, here you are having capital G. Don't think that they are having the same dimensions. This is different and this is different. This is acceleration due to gravity and this is universal gravitational constant. From where can we get this? How can we write the dimensions for this? What makes us easier to write the dimensions for this? It is impossible to remember the dimensions for all the physical quantities as I said you. So it is by using F is equal to G m1 m2 by d square. Universal law of gravitation. Okay. So from this, I have learned this earlier. Universal law of gravitation in your 9th class. So there you came across this, how to write the expression for universal gravitational constant. F is equal to G m1 m2 by r square. So this is the force and this is what your G here, and m1 m2 are the masses and d is the distance, it is nothing but the length. So what you want here, you want G, isn't it? So G is equal to F. This m1 means mass, m2 means it's also mass. This m comes here and m comes here, it is m mass square, and this length square goes to the numerator, so it is L square. So already you know the dimensions of this here. This is L square and m square, and you can complete this. Okay. So for small g, it is nothing but the acceleration. For capital G, it is universal gravitational constant. It is a constant. It has the value and as well as the units. Okay. And we can write the dimensions in another form also for this. For example, if you are finding any constant like this, if you are having a constant like this, for example, we got it here, universal gravitational constant. So we can write the dimensions by looking at the units behind the value. If we just look into this, the value is 6.67 into 10 to the power of minus 11 Newton meter square meter square per kg square. This is the value of G. You have learned it. If you remember this value, automatically you can spell out this unit also. What is this Newton? It is force. What is this meter square? It is length. What is this kg square? It is mass. Okay. So this is, from this it is F, from this it is mass, and from this it is length. Sorry, this is meter square means length square, and it is kg square means it is mass. From that also you can write down. So if you are able to remember the units, from units also you can write down the dimensions. Similarly here, what is the value of G on Earth? It is 9.8 meter per second square, isn't it? So this is the unit. What is mass? So meter per second square, this is length, and this is second square is time, L by T square, L1 T power minus 2. So like that also you can write. If you are able to remember the unit, from unit also you can write down the, what is it? The dimensions. And here also resistivity. You might have well learned about the unit of this resistivity. It is ohm meter, isn't it? This is the symbol for resistance and this is the meter, means for length. If you remember the formula for dimensional formula for resistance, so write the dimensions and into this is length L. We will get the dimensions for resistivity. Okay, by using units, we can also write the dimensions in that manner. Coming to the another physical quantity here, the power. You can easily remember the formula. Power is rate of doing work. Rate of doing work. That means work by time. So write the dimensions of the work. As you know very well, W is equal to F dot S, and time is time T. So the dimensions here written as T like this. So the thrust. Thrust, what is thrust? So here thrust is nothing but the force, the perpendicular force acting on a surface. Thrust is nothing but the force. So we can write the dimensions for the force for this thrust. It is the perpendicular force, that means it is also a type of force. So like this you can write down the dimensions for this. What is tension? Tension here means that you don't feel that tension means some nervous tension or something, like that. Work tension, or that is not the tension here in physics. Tension means here, suppose if you are having a string and if you are hanging something to it, so this will be tight, and in this you can see the tension. That means it is a type of force. A type of force. So tension is a force. What is stress? Stress is force by area. That means nothing but similar to the pressure. After knowing this formula, just don't leave it like that. Just go for a practice for writing the dimensions. And two other things are remaining here. One is the wavelength. Wavelength, you know, it is lambda. Wavelength, it's nothing but the length. So here L1. That's all. No unit, no dimensions for mass, no dimensions for time. Simply you can write as L1. Frequency. Frequency. What is the definition for frequency? Number of cycles per second, isn't it? Or number of waves in 1 second. So number of cycles means this is a number. Number has no dimensions, so I am writing it as 1. Second, this is the time, so it is t. So it is t to the power of minus 1. Okay. So these are the important physical quantities, and just practice all these physical quantities, and next we'll come with the uses with the dimensions. Okay. See you in the next session.